Awesome.
Okay, I'm going to do a very brief introduction and then turn over to Sterling. Sterling has been a phenomenal graduate student. I met him in 2018 when I actually gave a seminar at BYU, and he was one of these students that was either a master's, I think, or an undergrad at the time, and he came up and had lots of really great questions. He was really curious and sent follow-up emails, and so it was a no-brainer when when he showed interest in a PhD program to invite him up to the U, and I'm sure glad I did. Now, that said, he started in 2020, which, the world was like totally locked up. And so it was a weird time to start a PhD program. And yet, notwithstanding, labs being closed and everything being online, here we are in 2023, and he's defending. So that's just 3 years. That is very atypical for a PhD student anywhere to finish their program up in just 3 years. But you'll see that we didn't accomplish that by cutting corners. Sterling has accomplished an enormous amount in that brief period of time. And since June, he's actually been up in Canada. He's left us for the great frozen north and gone to Toronto, the Acceleration Consortium, where he's now currently serving as the director of trainings and programs, which is perfect fit for him. And they're lucky to have him, I feel like. I could go on. I could say many things about how wonderful he is. He had a kid during this time. He has trained countless group members and undergraduates. He's been an advisor's dream student, and I'm just so excited for him to tell you what he's accomplished. Well, part of what he's accomplished in today. So I'll shut up and turn the mic over to Sterling.
Awesome. Thank you, Taylor. I am really glad that you're all here, and I'm really excited to talk to you today about data-driven materials discovery with 3 main focuses here. We've got novel discovery, Bayesian optimization, and self-driving labs. And I'll cover each of those in gory detail. First, just a quick note, we discover new materials. So what's this materials discovery thing? We discover new materials, new alloys, new drugs, new polymers, not because we need to, but because we have the capacity to do so. So let's take Corningware glass, for example. We've got Donald Stuckey, who accidentally discovered this Pyrex glass via furnace mishap. In his words, the temperature gauge was stuck on 900 degrees and I thought I had ruined the furnace. I grabbed some tongs to get it out as fast as I could, but the glass slipped out of the tongs and fell to the floor. The thing bounced and didn't break. So this is, a Pyrex Corningware glass discovery. And materials are discovered through a variety of means, kind of like this one. They've got mistakes, like glass or vulcanized rubber. We have alkaline batteries or incandescent light bulbs that come out of sheer perseverance. You have kind of the right time and the right place. With the Teflon discovery, they noticed one of their gas cylinders just stopped flowing air. They cut it open, hopefully safely, and found this substance inside. Other times it's attention to detail. Like with stainless steel alloys or shape memory alloys. And then we have nature-inspired things as well, like Velcro. We also occasionally have things that are discovered from unsafe lab practices, as a scientist, while having lunch, notices a very sweet taste on his fingers while he's eating his sandwich, and then rushes back to the lab to figure out which of his random vials, like tar-based substances, had produced this deliciously sweet sensation in his mouth. And more about this, if you check out Taylor's YouTube video, How Are Materials Discovered, goes into a lot of detail about each of these, some really neat use cases and stories. So then we bridge into materials informatics, this combination of material science and data science to help accelerate the discovery of new materials. So for example, using some machine learning models, Taylor and others were able to discover 2 new candidates for super hard materials. Those 2 listed below, doing this high throughput screening, and validated those experiments in the lab and found a new super hard material. And I have a rundown of about 50 of these experimentally or computationally validated machine learning studies, materials informatics studies, that you can look at a review paper I wrote very early on here that looks at all sorts of different techniques that are used and then all sorts of different applications that they were used for and then validated. So like I mentioned in the title slide, there are three core thrusts that I'll be looking at as part of data-driven materials discovery. So first is novel discovery, second is Bayesian optimization, and the third one is self-driving laboratories. So first with novel discovery. Discovering materials that are very close to what we've already discovered is low risk, but it's also low reward. And so to find truly transformative materials, we have to start looking outside the existing set of known materials, no longer do local optimization where we make slight tweaks, but look into somewhat wild things, but have that in kind of a structured way. Second, with Bayesian optimization, we've been doing traditional design of experiments for hundreds of years, if not millennia, where we're trying to decide our search space, do it all at once, test things out. There are more efficient ways, and Bayesian optimization is one of those highly efficient ways. And I'll be talking about how I've applied that to different materials informatics tasks and show how those can be applied to your own as well. And then we get into self-driving laboratories, which I think synergizes really well with Bayesian optimization and those advanced optimization techniques, because you take this kind of automated suggestion of new experiments where you're incorporating domain knowledge as much as you can with automated laboratory equipment to autonomously discover new materials, autonomously carry out those experiments, suggest new ones, do the full analysis cycle there. So these are the three main topics that I'll be covering here. Sorry, that was meant to be gone. So between 2022 and 2023, I have been first author on 10 manuscripts and 1 preprint. These are manuscripts all tied to Sparks Group funding, kind of under that umbrella. And I've co-authored 5, 3 are in preprint stage for a variety of journals here. And also, I've had the opportunity to present at about a dozen conferences, including in other countries. So Toronto, where I'm at now, Canada, many places in the US, East and West Coast, as well as a great trip to Vienna, Austria as well. So along with that, I've also created about 12 repositories, these Python-based packages or code bases that comprise in total about 40,000 lines of open source code. And that's 40,000, counting it up after all is said and done, not necessarily the in-between, all the prototyping, troubleshooting code. So when I did a quick estimate, is that I probably typed about 10 million characters into VS Code since I started my PhD, which is about a few thousand words, words per workday during that time. And I've contributed to a lot of open source projects as well, like Numba, Axe, Materials Project, PyScaffold as well. So kind of co-developing and, in addition to being a user, trying to make contributions. This happens with a lot of support, and I've had an awesome opportunity to mentor some students like Marianne, Tran, and Colton here, as well as kind of carry the torch as a lead materials informatics student with Hassan, Ramsey, and Trupti coming in close behind, and then working with a number of others as well on different projects. So first, I want to talk about this novel discovery bit. This is the first main thrust, if you will, of the talk. And so this is kind of the classic example of, it's called like the drunkard search problem, or the streetlight effect. So where do you look? You look where the light is. So, this police officer says, oh, is this where you lost your wallet? No, I lost it in the park, but I'm searching here because I can see. And that's what we do with materials discovery a lot of times. And so I want to talk about a technique we can use to try to push ourselves outside of the known, the existing materials that we typically see. So first, we'll start out with a set of chemical formulas and some target property. And we're going to split that into 2 categories, our training and our validation. We're going to use the training to build the model, and then we'll use the validation to see how the model performed. And we'll use something called the element mover's distance, which is a way to say how far is this particular chemical formula from this other chemical formula. So if you do that pairwise for a list of elements, the distance between zirconium and zirconium is 0, of course, but then you get distances between all of the other ones as well. So we build this large chemical dissimilarity matrix. From there, we can assign these, embed these distances into a two-dimensional space so we can visualize it a little bit easier. And we do that using a tool called UMAP, or one of its close variants, DenseMap here. And so we get this kind of density-aware embedding of our chemical formulas. From there, we can assign clusters, look at clusters of elements that are similar to chemical formulas that are similar to each other. And from there, we can take a look at the optimal trade-offs between the performance that was predicted for a particular formula and its chemical uniqueness according to the criteria we defined earlier. And so where you see this trade-off that there's no one best solution that dominates everything else, the thing that has the highest performance may not necessarily be very unique. Likewise, the thing that's most unique may not have high predicted performance. So we can look at some of those trade-offs there. We can scale those values to try to come up with some overall number, taking a weighted sum of those numbers. And
hey,
then,
Sterling, can I just ask you a quick question? First,
please put it in the chat. Please put it in the chat, Mike. Thank you.
Okay.
So the top 2% for this validation held out the top 2% of bulk modulus performers here. So with this, essentially, it's like, okay, what if we hadn't discovered this top 2% yet? So we hold that out as our validation data, and we start looking through, what, if you take random search, you take random search, you take the performance metric, you kind of weight those differently. When you're looking at this kind of weighting of high performance and chemical novelty, you're getting kind of a good mixture in between with that one. So please excuse this slide. From here, Matt discover, but basically what that showed is that we're able to get kind of run this in an iterative fashion to identify new materials and find ones that are both high performing and chemically novel. This is wrapped up into a nice Python package that you can install with a single line of code. And it has documentation and all the bells and whistles that you'd hope for in an open source.
Hey,
package.
well, we're at a break point here real quick, Sterling.
Yeah,
I
please.
want to handle questions. We typically ask them in real time during a defense with some additional ones at the end. Do you want to save them at till the end or at break?
That would be my
point?
preference. There's a Q&A tab. So I'm open to what you want on that, Taylor, but I figured the Q&A could help out, or we can stop at the end of each major section.
Yeah, you've got your 3 chunks of your, why don't we do that so we don't get too far from them? We can populate the Q&A tab with questions as we go, and when we get to the end of each of those, why don't we pause for questions? Okay.
Sounds good.
All right, so I'll have you keep going then.
Yeah, perfect. So we've been using this tool for a variety of applications. So we've got Colton Simuler here, who used it to do screening for high temperature superconductors. So we've got LK99, Big Buzz, and this paper actually just got published maybe 2 weeks before LK99, the announcement came through. And so it's kind of this idea, okay, how different is LK99 from everything else? Are those justified results? Probably not. But we can kind of take a look at some of these new materials, new discoveries in that context, and run it through some of these techniques in addition to trying to verify it experimentally in the lab. So we're using Discover for a number of applications. I mentioned the superconductivity one, and as well as a super hardness one that Marianne Liu is spearheading. She's been doing some experimental validation of our predictions in the lab, and so more to come on that. So here we'll take a pause, take a break, and open up for questions on the novel materials discovery piece.
Hey, Sterling, it's Mike. Yeah, sorry. Sorry, I was having technical difficulties getting in. But I wanted to ask about I was just curious about how you determine the chemical similarity, because your matrix was showing like single elements as well as, you know, kind of higher order combinations of elements, especially it looked like metals. So can you just say a few words about that?
Are you familiar with the Earth mover's distance, or the Wasserstein distance?
No, I mean, I assume it has something to do with like electron affinities and something like that.
No, not at all. So Earth mover's distance, you've got, think piles of dirt. You know, you're sitting there, there are, let's say, 3 piles of dirt, and you want to arrange them into a different distribution of piles of dirt. There's a physical, you know, there are like units of work involved with every shovel that you have to make and every step you have to take to efficiently move one pile of dirt, or, you know, several piles of dirt into another distribution of piles. Not going into the math behind that, but that's the concept of Earth mover's distance. It's like that quantification of the amount of work to move something, you know, one distribution into another distribution. So when we represent a chemical formula as a distribution, in some sense, you kind of see here with the ants on the left, you know, lithium has some height on this distribution. There, you know, you can use atomic number to kind of weight the x-axis of this. So it's like, you know, okay, atomic number, and then the height is the fraction of the element within the whole formula. So that's one way to represent it as a distribution, and then calculate that work or distance between. So that's how these.
But like like, I mean, does it have any tie to traditional chemical concepts? I mean, what you just explained doesn't, for me, answer like physically what's going on. Like, how do you determine this height? I mean, like atomic number is one thing, but I mean, the periodic table has been pretty well established. So there's cycles in atomic number on the periodic table.
So that one's based on the modified Pettifer scale. So instead of atomic number, we're using modified Pettifer scale, which has been shown, used in different contexts to show that if you have to represent elements along a one-dimensional number line, this one probably does better than atomic numbers for most use cases. So that's one piece, and then it's you know, kind of gets more into that. But that's a great question, and in a lot of ways, you kind of think of it as Euclidean distance, where that is very typically used for almost all distances, but this one gets a little bit more into this kind of concept of moving distributions. It works really well in a lot of other machine learning applications, which I think is why the original inventors of this one brought it into materials informatics, tried it out. The clusters that they saw, the way it grouped things, seemed more chemically intuitive to them, and they wrote about that.
Okay, so it works. I mean, can you comment on like how well something like this works for like metallic alloys, ionic compounds, and covalent compounds?
That's a good question. No, I'll probably embarrass myself if I answer that.
May, kind of extend, since my questions are aligned exactly the same way. For example, if you apply it for the intermetallics, would you be able to reconstruct anything resembling the Hume-Rosary rules for the metallic alloys?
Yeah, so I'm familiar with the Hume-Rosary rules, but I haven't personally implemented that in any specific context. Like, okay, let me just look at metallics. Let me just look at you know, ionic bonding, things like that. It's a great question. I just I haven't approached element movers distance in that context.
Sterling, maybe a follow-up that kind of gets at what both these other folks are asking. What are the limitations of this particular descriptor, and where do you think it could go from there?
Yeah, definitely. No structure. that's by and far the biggest limitation of it. You get kind of two camps in materials informatics. There's people that say we can crystal structure is really hard to measure. We don't always have it. And sometimes it's hard to represent complex microstructures. So we just use composition because it's what we have. We do it. And then the other camp is, well, without crystal structure, you basically don't know anything, carbon being the quintessential example there. So I think both camps have produced meaningful results. For me, it kind of started out more on the compositional discovery side. For example, the superconductivity database, no crystal structures attached with that, but you have around 20 to 30,000 different compositions there. You might only be getting somewhere between 100 to 1,000 if it's like pure crystal structure based ones. If you move into that, and Chris knows all about the superconductor discovery. In terms of limitations, there's some other ones, other representations that take more of a, I guess, factor in higher order relationships. So grid RDF being one, where it's trying to kind of have this matrix of interactions between multiple elements rather than just saying, like, okay, each element gets this one number.
I covered my question. Thanks, Sterling.
Yeah, I put mine in the Q&A, but you kind of covered them. I am curious, so grid RDF could be a tool. How far are we to actually implementing that?
Oh, I'm glad you mentioned. It's ready to go. It's been tested to make sure it works. Haven't run a full study on it. So Discover 2.0, it's been adapted to where you can swap out crystal structure predictions, crystal structure distances, and run it through all the same machinery that's there underneath it. So if anyone's interested in trying it out, lots on this thing.
Are there other questions on this first segment of the talk? We can always circle back at the end. Otherwise, yeah, in lack of any, if think of other one, feel free to drop in the Q&A. We can do them at the end, but let's move on to the next section then.
Cool. Okay, so core area number 2, Bayesian optimization. There's this quote from Citrine Informatics that I really like. Not all experiments are equally useful. Some experiments provide more information than others. And so we saw that a little bit with the Discover algorithm, that some materials are much more novel, some are much more high performing. We may not be getting a lot of benefit from always just tuning small variables. So there are trade-offs. And so this part really gets into adaptive experimentation as a more efficient version of design of experiments. So with kind of typical, traditional design of experiments, you design all the experiments at once, and then you observe all the outcomes at once. So there's no loop or cycle there. Whereas with adaptive experimentation, you iteratively design, suggest experiments, observe the results, factor in those, account for those results, update your beliefs or your model, whatever it is, and bring it back in a closed loop. And I like to use the analogy of cutting down a tree to talk about the different design of experiment methods. So grid and random search might be like a hatchet, gets the job done. Quasi-random search, more like a chainsaw. And then with adaptive experimentation, you start getting the efficiency of the tiger cat. This is very efficient ways to reach some objective, some target there. So in terms of what this looks like, you've got your typical grid, evenly spaced points across the different axes, random, you randomly pick. Whereas quasi-random search starts to get into ways where you can a little more, you can just distribute the points with fewer pockets, big gaps there. And then with adaptive experimentation, you start building a model, trying to decide where the optimal next point to search is. First, we'll talk about the first two methods I mentioned. And these quasi-random search methods have the best of both worlds compared to grid and random search. So first, let's just take a look at grid and random. And then next, the quasi-random. So with grid, we get systematic large gaps in our search spaces. With random, we get large occasional gaps. Whereas on the other hand, with hypercube or Sobel sampling, these quasi-random search methods, we tend to get smaller pockets that are less systematic as well. And these methods tend to have lower discrepancy than grid or random search. And what I mean by discrepancy is they have a higher uniformity. Now that's not uniformity in a grid sense, because remember those give us big pockets. Essentially, low discrepancy means you're doing a good job not having like these big gaping holes in your search space. And you can see that at the top here where we've got something like 100 data points laid out there. The ones on the far right look more evenly distributed. And the size of the pockets increase with the number of dimensions. So in one dimension, your max spacing between any 2 points is 0.5 in this case. As you get higher and higher, the max distance between any 2 points increases. And so this becomes a real problem with high dimensional Bayesian optimization. Let's say you have 10 or 20 parameters that you're trying to optimize. Your pockets are very large. So to use something like grid search can actually come back to bite you with a lot less efficiency. And like I mentioned, real world material science tasks, they typically fit into this low budget, many dimensional space. And so we get, kind of seeing with more and more dimensions, like up to 20 dimensions, time and time again, the quasi-random search methods are winning out. Okay, so moving into adaptive experimentation a little bit more. This is a technique that uses prior information to inform future decisions. And you kind of visualize it in this graph. You initialize some search space or campaign. You design, kind of suggest what your experiment's going to be. You design it. You run the experiment. You analyze the results, and you bring that back in a feedback loop until you reach some ending threshold for the campaign. And there are a couple terms I want to go over. First, we have acquisition functions. Those are functions that guide how you should search the parameter space. Essentially, that's all in the design piece. And acquisition functions are often this trade-off between exploitation and exploration, where exploitation means focusing on the current best results, and exploration means looking towards unexplored regions. And Bayesian optimization is a technique that efficiently balances this trade-off between exploitation and exploration. And so, we start talking about statistics and expectation values, Bayes' theorem and all that, but essentially it's rewarding when your predicted objective along with some certainty is better than the current best by some amount. And you can start seeing that in practice with expected improvement as an acquisition function along the bottom. So in the top, we have the blue with the mean predictions, black is the data, and then the bands are the uncertainty estimates on it. And if we plot the expected improvement acquisition function along the same x-axis parameter, and we look for the maximum value there, then essentially what that's saying is we should pick our next point to sample from at like 2.8 or something, where you notice it has a large variance and also relatively high prediction. And so you get kind of this trade-off. And mathematically, that's sort of the elegant way to balance those two values. And so this continues in an iterative fashion where you add new data, recalculate the acquisition function, bring it back in. So And there are many other functions in addition to expected improvement. You have upper confidence bounds, and you get into some acquisition functions that are really well geared towards like high dimensional problems, some that specifically take into account the cost of an experiment. And so I'll get into some of those a little bit later, but there's a lot of expected improvement is often the default, but it's not the only choice. Okay, so now moving a little bit more into the comparison between these, we've got Bayesian optimization and those 4 methods I showed. And in this simple 2-dimensional function, it's just basically a analytical formula, very simple one. You can see the log scale here with the different peaks that we're looking for. With this, when you apply each of these different search methods, grid is the least efficient, random is significantly better than grid, Sobol, then Latin hypercube, with the best by a long shot being the Bayesian optimization here, where you're trying to find one of these minima. Similar trends hold when you go into higher dimensions. So this is a 6-dimensional analytical function called the Hartman 6. And you start to see that even more clearly, that after about iteration 10 or 11, where the Bayesian optimization is kicking in, you gave the Bayesian optimization a few initialization trials, and then it's kicking in, it really starts to lock into the minima there. And now I want to provide a little bit of motivation for why Bayesian optimization, and specifically advanced Bayesian optimization, is so important for industry relevant materials discovery tasks. So with this, we've got multi-fidelity problems. So you could think of a thermocalc simulation being, this physics-based simulation. It's costly, but it's maybe not as costly as running a physical experiment on an instron and going through a sample prep. To Mike's question real quick. I think Mike and Sergey would have a great conversation about this. Oftentimes, the assumption is that the prediction is just a flat line when you're doing Bayesian optimization. That's your prior information, just a mean flat line everywhere. One of the things that Sergey does a lot is, instead of having it be a flat line, you impose domain knowledge, physics-based constraints, and other things to, instead of a flat line, have that follow kind of your expected intuition and then build off of that. So for here, we're talking about multi-fidelity. There's multi-objective as well. So with an alloy, if you're looking at mechanical properties, you've got yield strength or elongation of fracture, and these are competing objectives. There's not, as far as we know, one material that has the best in all of these categories at once. You also have a mix of continuous and categorical variables. For example, like, was this alloy cast or was it wrought? What was the manufacturing method? We also have these constraints, very simple constraints like everything sums up to 1, can be actually kind of difficult to implement in an optimization sense, especially when you're dealing with high dimensional search spaces, where maybe 23 different elements are represented in the whole set. And you throw in this big wrench into the chain of things that often you have chemical parsimony at play. For materials problems, you can't or you don't want to mix dozens of things together all at once. You only want to mix 6 at a time. That might seem straightforward when you're in the lab, but for an algorithm to really capture that smoothly with so many options is pretty difficult. And I want to go over a few case studies to highlight those different aspects of advanced Bayesian optimization. So the first one is focused on this high dimensionality. Second one is on constraints and packing and reducing your search space to be as efficient as possible. And then the third one is this kind of toy demo of autonomous experimentation. And I wrap those all into this optimization benchmark as well, which I'll talk a little bit about later. So first, the high dimensional optimization. So we've got this model called CRABNet, and a legacy model in the Sparks group, still seeing a lot of good use, maybe from like 3 or 4 years ago. And there are 23 tunable parameters in this model, little knobs that you can change to try to make the model better, make the model easier to run, less expensive, et cetera, et cetera. And there are lots of different types. So you've got integers, you've got floats, continuous numbers, true, false, so like these Boolean or binary, and categorical ones as well. And so we've got 23 with a mix of all those different types. And I used CRABNet to predict experimental band gap for a materials science benchmark task on MathBench, if you're familiar with that. And when running this model, SASPO, which imposes these, we'll get a little bit math here, strong prior assumptions on the inverse length scales associated with the Gaussian processes. Essentially, it makes it hard for the model to overfit and just like be super confident, because that's one of the main issues with models when you get into high dimensional optimization or modeling. Models tend to be very confident, overconfident. And so with this one, we can take a look at these kind of feature importances for each of these 24 variables, 23 variables. So with this first one here in purple, you'll notice that it has a high inverse length scale. Let's see, am I saying all right? It's non-smooth. So if you look at the model error, which is our objective in this case as a function of the parameter, you see a valley there. It's not Nebraska. It's more like the Rocky Mountains or Death Valley or something like that. And as you get lower and lower in terms of feature importances, you start to get a lot smoother behavior. And basically what that's saying is that the very bottom one is not very informative, whereas the top one really affects the outcome of your model. So there's a lot of great interpretability that can come from looking at these Bayesian models. And in this specific case, using SASPO with CRABNet led to a 12% decrease in the kind of new record for the task. So better than relative to this initial very fine-tuned but manually fine-tuned example, bringing that hyperparameter optimization, set a new record and brought it down significantly. So the second case study, yeah, go ahead. Yeah, please.
Sterling, just the thing, I think I understand what you just walked us through, but can you give us some concrete information on what class of materials were you looking at for the band gap, and whatever that first parameter is, what is it? what
oh, the first parameter, sorry, that's so embedding scalar. What I want to make clear, and I'm glad you brought up, these are not physical parameters, these are machine learning, not physics-based ones, these are machine learning-based ones. So it's the idea that you've got this very high dimensional space for the machine learning model, and you're using that machine learning model to predict band gap. So how do you adjust the knobs on the machine learning model to try to get better predictions on it's 5,000 different band gap materials?
Okay, and what features, or what I think I'm asking this question correctly, what are the strong elements in the feature vector that correlate with band gap?
So you're talking about physical properties or this underlying representation that correlates well with band gap?
Yeah, so these parameters you're talking about here are sort of how you tell the machine learning model to run its process, but what were the inputs that went into the actual model?
Yeah, so for CrabNet, and this gets a lot into Kai Kawei's dissertation, his building up of the CrabNet model, where they use mostly mat to vec is what it's called. And if I remember this correctly, mat to vec is based on, and David, please correct me very soon if I embarrass myself here, literature-based, was that one abstract-based? So you take all the abstracts for different things and you look at kind of this literature, natural language similarities between different elements and different contexts. So is this completely machine learned representation based off of abstracts in scientific articles, capturing that in a numeric representation, similar to how tools like ChatGPT, transformer models, text prediction, at some point they all have a numerical representation for the text there, and they evaluate similarities between texts. And mat2vec is that based on a large corpus of scientific abstracts. So for that one in particular, feature importance really washes out, because feature number one from the mat2vec representation doesn't have an explicit physical meaning. There are other ones that do have more physical meanings, where you start talking about density or electron states, things like that.
So, okay, if I understand what you I guess what I'm kind of inferring from what you're saying is like if there's an abstract of an article and it has a chemical formula for a compound and then a band gap mentioned, those two things get associated. So I would translate what you're saying,
and a slew of other properties to make that representation.
Okay, so there, I mean, because that, yeah, to me, I guess the question that I want to ask based on that is it kind of sounded like you're saying that essentially chemical formula can be used to determine band gap without any other information about crystal structure and bond length and electronegativity and so forth. So is that a true statement or a false statement?
Oh, both. So with the, let's see where I go. You can get some mileage without the structural information. But if you want the full mileage, then get the structure information. The question is the cost of getting that information worth the improvement in your discovery kind of match? Maybe think of it as low-hanging fruits. If you just look at composition, you have a huge data set that you can work with, and you can kind of screen and identify certain regions that might be more interesting based on certain chemical formulas. And then when you actually go in the lab to synthesize it, you characterize the structure. But a lot of people avoid composition-based optimization or machine learning because you lose out on so much information there.
So specifically, I mean, you showed that your way of doing things produced a really good result. This 0.33 in whatever metric you were using. What did you do? Did you have just composition? Did you have something about crystal structure or bond length or bond angles or what's
chemical formulas? That's all I used. I have other work and a set of about 30 slides that I removed from this presentation that gets all into the crystal structure stuff. So maybe I'll need to send some of that to you aside from this. It's also in the dissertation, but yeah, a lot of this is composition based. So chemical formulas and identifying tools or algorithms, metrics that have been shown to work well for chemical formulas, and a lot of times making those better, combining those with other algorithms. But I think a lot of it kind of goes back to the robustness of the benchmark task itself. What were these what were those 4,600 points? Was that a broad enough sampling? And the main thing here being these are experimentally measured band gap values. So not all of these experiments would have like the structure fully characterized necessarily in order to make some of these measurements. There is a task that has like 120,000 points. It's purely simulation based. And so no experimental work there. And that one has its own benchmark task there, where you have like 120,000 DFT simulations essentially. So yeah, my focus being more on this one.
Okay, thank you.
Yeah.
Sterling, before you move on to the next case study, while we're here talking about high dimensionality, I'm just curious, maybe we did this in our paper and I'm forgetting it, but you know, there's lots of ways to tune hyperparameters and Bayesian methods are out there. SASBO is just one of them. SASBO intentionally it takes into account this high dimensionality. How do we compare with just traditional, something like a ray tune or something approach to hyperparameter tuning?
Yeah, so a really good normal Bayesian optimization, so like kind of classic Bayesian optimization, but very well done, is right here. So you go from like around 0.375 down to 0.355. So it gets you maybe almost halfway there compared to what you can get with the high dimensional optimization. So it's better. It's better than the default or starting point, but there's a lot of additional room mileage. And this one also wasn't this isn't the state of the art. It did better, but if that's not even better than the best, was it really worth kind of that improvement? In this case, it's like, okay, we dropped it lower, brought it to be better than any of the other submissions in the bunch. So I think that's all pretty, for a model that's existed for like 3 or 4 years already. I think that's kind of the part.
Thanks,
and then, yeah, Chris, you mentioned the polymorphs. So with this MapBench task in particular, a lot of times when I deal with data sets that have polymorphs, I tend to take the polymorph that has the highest or the best performance value for that, kind of this idea of included. If the model gets it wrong, maybe it's not so bad because it's just a prediction, but we don't want to throw out potentially very interesting spaces. So for example, with carbon, if we're talking about bulk modulus, I'd put in the bulk modulus for diamond rather than the bulk modulus for graphite. That's how I typically do it. With the experimental band gap task in particular, I think that this was just based on a sampling of scientific articles, large throughput. I don't know if they had articles that overlapped with polymorphs. I don't think they did, but if they did, I could definitely check them.
Thanks, Sterling. I clicked on the link and I realized it was someone else's aggregation, so that makes more sense now. Thanks.
Sterling, I had just a quick question. Can you guys hear me? Yeah. Okay. So when choosing an acquisition function, say when looking at like expected improvement versus UCB, is there scenarios where you would choose one over the other, or is it just kind of try an acquisition function, or just try them all and see what performs better with your data? Or how do you go out there like a method to choose an acquisition function? Because there's kind of quite a bit of different ones that almost do the same thing depending on the task. But that's something I've kind of encountered in my research, where I kind of get stuck trying to figure out what's the best method to select an acquisition function for the problem.
Yeah, that's a great question. So for me, first off, I'd say the results always, results that have been rigorously evaluated, carried out, comprehensive benchmarks. For me, if I don't see a benchmark that's as close as possible to the thing I'm trying to do, and it shows, hey, this one does better than this one, I take it with a very heavy grain of salt. For So a lot of times I'm running those kinds of benchmark studies myself when I'm trying to make an important decision, like, okay, I think there could be a really big difference between setting up my model in this frame versus this one. I've already looked, I haven't found anything quite close enough for me to make that decision. And so that's where this idea of creating benchmark tasks that are as close as possible, that look as and behave as close as possible to the one you're actually trying to do, there's a lot of value in doing that. Aside from that, because that takes time to run these benchmarks, there's not always a great data set and set of property values corresponding to it where you can run these very well. And so with that, then I go to best practice and intuition. I think that expected improvement is a great default choice. I think that, when you switch to things like upper confidence bound, the mileage will pick. If you don't have a good way to assess which one's better, pick one, keep it in the back of your mind. If it's not performing well, swap it out. But really, for me, it's about the benchmark tasks. It's about running these comparisons in a setting as close as possible.
Awesome. Thank you, Sterling.
So next, I'm going to be talking about one of those benchmark kind of scenarios that I talked about, which is how do you represent your search space? So an irreducible search space is like one that has less hay and a smaller needle, where the needle is like the solution. Don't take this analogy too far in optimization, and then the black line is like your search space. So you're searching within this black rectangle for somewhere along this line of the needle. Very simplified. And so a few questions I'll pose to you. What's easier to find? A point in a line in a rectangle, or a plate in a box? So if you were like little Mario in a one-dimensional or a two-dimensional or a three-dimensional world, and you were looking for the point, the line, or the plate, which dimension of Mario would you want to be? And say you want to be in the line. You've only got two ways you can go, and you're bound. If you go down one of the ways, you're bound to run into the dot. Okay, what about this? A line in a square or a point in a line? And so kind of the same line of thinking applies. You've only got this kind of one direction that you can search. It constrains you to run into the area a little easier, perhaps. Now, one that's maybe a little less obvious, would you rather search for a pepperoni slice in a pizza with 6 symmetric slices, or in a single slice? And the answer is, it's not entirely clear when you have this like symmetry in your search spaces. And these are all constraints that frequently manifest in materials informatics tasks. So for this one, it's like a unitless physics simulation, dimensionless physics simulations, where if you multiply all the numbers by a constant, the result is still the same. We have compositional ones where with like chemical formulas, have basically the sum of all the constituent components adds to 1, and you can represent that in a way that you might have 3 things you're adding together, but if they all sum to 1, then really you only have 2 degrees of freedom or variables that really affect things. And then we have permutation ones. So this would be like you can swap out aluminum and oxygen in the representation, and it's still the same chemical formula or the same mixture formulation. Okay, these are the 2 I'll be talking about here. And these apply by definition to all formulation tasks. And implementing those constraints all together is quite difficult in practice. I actually kind of became a co-developer of the software that I use, because as I was asking questions about how to apply these to these more materials informatics specific tasks, I started running into issues, and would actually work with the developers to actually change the code base to make it easier to use for materials informatics tasks. And so, between like 15 different threads and maybe something like 120 plus comments, just dedicated to this idea of constraints within Bayesian optimization, kind of coming, gathering that knowledge into the implementation. So with this case study, we've got maximizing a simulated packing fraction where you have 3 types of particles. So you can imagine you've got 3 jars, each of them have their own particle types, sizes, distributions, and you say, okay, I want to take 3 scoops of this one scoop of that, 1 scoop of that. And this is, so it's kind of like a classic formulation task in that sense. And this is applicable to things like solid rocket fuels, where the packing of the propellant, the fuel inside, affects the burn rate and other things. And what I'll be focusing on is just the geometry of it. So I'm not taking into account friction and like chemical interactions. It's kind of this, like hard spheres stacked together. And depending on the parameters for the simulation, it could take somewhere between 20 CPU minutes to 20 CPU hours. Becomes very expensive very easily. And we represent these 3 distributions or 3 particle types based on these distribution parameters. So we've got 3 that are at the very bottom, the P, this is the composition. The fractional prevalence can range from 0 to 1. And then we have 2 parameters per particle type that are effectively mean and standard deviation, though they have slightly different mathematical definitions, but you can think of it like that. And so in red would be like the first particle type with its own distribution, and then green is another particle type, and then blue is its own, and that gives you some kind of overall distribution of particle sizes, which all get thrown into the simulation box, and then you figure out how densely packed it is. And so this has the 2 constraints that I mentioned before, composition and permutation constraints. And these are actual visualizations of those constraints, where you've got P1, P2, P3. And if this were the solution, then when you compact or reduce that representation, now you have a triangle with a point that you're searching for. So instead of trying to search for somewhere along this line in this 3-dimensional box, you have to just look for the point in a triangle. And then same kind of thing with the pizza slice over here. And then we use, I'm very partial to Meta's adaptive experimentation platform. It's built on a lot of state-of-the-art tools. It's well-maintained, developed, open source. And when I was running this benchmark, I ran about 2,000 evaluations of this simulation across 10 campaigns with 50 iterations for each campaign. I had 5 workers or CPUs that were allowed to run these simulations during the search. And then I was comparing the different combinations of constraints. And just a kind of quick aside about how the optimization went forward. It wasn't sequential, so it wasn't that I took one experiment, fed it back into the model, waited for that, took another experiment, and went on iteratively. I was producing batches of experiments, but asynchronously, where as soon as one worker was done, so like, okay, I give my data back to the model, instead of just sitting there idle, waiting until the next batch, immediately the algorithm suggests a new point for it to start working on as it becomes available and based on all data that's available so far. So asynchronous optimization is really important when you have experiments that might take a little bit of time or a lot of time depending on the parameters. So in this case, where it could take between 20 minutes to 20 hours, using asynchronous optimization allows you to reduce the downtime of your equipment. Mike, what's up?
Sterling, it sounds like you've done some really good contributions in this field. I guess I feel like we've strayed pretty far away from anything that has to do with materials. I'm not sure I even understand the problem or the effectiveness of whatever process you just described having computed. Like I get that you've improved this algorithm or this method for optimizing something, but what was optimized and did it translate to better rocket fuel or not?
Jason might still be on the line. He's the one who had access to the proprietary simulations, would have been able to take that to the lab for experiments. But as far as I know, no, it didn't create better rocket fuel. That's what you're asking. So what I'm hearing is, where's the material science? And where are the material science results? What are the new materials you discovered? How did you make them better? And what's the science behind it, right?
Yeah, I think that's about sums up kind of the direction I'm thinking here.
Yeah.
And I mean, I understand that there's a wide range of things done, with it, computational materials, or, some people's PhDs end up being about, constructing some fancy instrument. And I do believe that there's a wide space, but I do want to hear the connection, right?
Yeah, I'll give you one that I can't actually present on because of the confidentiality, but I worked with a company to help them develop new alloys. And so I built a Bayesian optimization model for them based on that, incorporated almost everything that I'm talking about in this whole Bayesian optimization section into a script. It's closed source, only they have it. They have full rights to it, but they're using that to make predictions, to optimize materials in their foundry. And that's going towards their supplier for these additively manufactured parts for the automotive industry in particular. And that's about all I can say there. But hopefully that conveys that these tools are useful. They do have applications. For me, the answer of which tool to use is rarely obvious. And I see so often that people are using the simplest thing just because they can understand it, when there are state-of-the-art methods in computer science that are like a decade ahead of what's being used and published in like 2023 for these different articles. So a lot of what I'm trying to do is close that gap between the 10-year gap between state-of-the-art computer science, machine learning, and applying those directly to current materials informatics. I would have loved to have presented more on the alloy stuff, but that was one of the there. Does that help a little bit with that question?
Yeah, it does. And I mean, I like the way you framed your work. And I think, that is the kind of thing that can really, move a field forward.
Yeah.
I think the hard thing from my point of view is just how do I we just don't seem to generate enough data fast enough to make these huge scale things useful. And I'm trying to, I think that the challenge, Taylor and I have talked about this for a long time, but the challenge is always the matching the problem with the technique. And there's certain problems or these benchmarks that exist where you can actually benefit from these large scale things. And I guess a lot of the things I'm thinking about are what comes next is interesting to me, because I feel like the work you guys are doing has just scratched the surface on the actual hard material science problems. So I'm really interested to see what comes next. Like interfaces for me is one. Like how, when you put this next to that, bring them together and maybe do some chemical process or physical process that modifies that interface, what happens? I mean, that's something that is incredibly hard to predict.
I spent 3 years for my master's developing models for grain boundary energy. So I'll talk about, and that's a 5 degree of freedom space if you just consider geometry, not even like atomic arrangements. And that was, yeah, like when you say it doesn't even scratch the surface, I think a lot of it is, okay, what are the tools? What are they capable of? What are the problems? What are the tools that match up? And people can choose a tool and figure out the problems that are really meaningful and impactful. People can choose a topic and then try to find the tools that align with it. I think the real danger is when somebody picks a tool and then they force the topic into it, or they pick the topic without really an idea of how they're going to bring it about. So I think, yeah, for me, a big question with my PhD has been, okay, state of the art in computer science optimization tools and kind of traditional materials discovery, where are the links and the matches? And there's a reason why super hardness is almost a quintessential material, like solid state material science discovery task, because you can mix a bunch of powders, arc melt them, and press them with a small, needle Vickers hardness test and get a value and kind of run that in a closed loop. And so
actually you can do that. I just been in PNNL that has a machine that in principle allows to do exactly that. So the rate at which things become possible is amazing. I mean, it doesn't take anything away from your argument, but once you get onto this needle of automated experiment and closed loop experimentation, I mean, you cannot do it in the lab and you cannot do it with the Raspberry Pi, but it turns out that you can take a $5 million commercial system that's optimized for certain type of machining, and all you have to do is to change the feedstock, and lo and behold, you have a platform for manufacturing with the combinatorial and the loop optimization. So the impact of the things that you are working on is going to grow super exponentially for the next years.
Yeah, great comments, great discussion. I think I might jump back in to try to keep making some momentum. Thank you both. Okay, these simulations, they're noisy, they're expensive, so high variance, exponential increase in cost of the simulation as you increase the number of particles in it. And I used a few metrics to try to decide, okay, did we actually generate something with higher packing fractions or not? So in sample validation, we just say, out of all the experiments we ran, which one had the highest predicted value? Repeat that experiment 50 times, say, and take the average. That's our metric for how it did. In sample predictions, this is kind of the poor man's way of evaluating. You just take the prediction for the experiment with the highest packing fraction, and that's it. You don't run any repeats, so you take it along with all its kind of noise embedded into the model, but it's cheap. You don't have to run any additional experiments there. And then we have model error, where we just say, okay, of all the data that I collected, if we kind of split up the data and try to predict on the bits that we held out, how well did we do in terms of model error predicting it? And on average, the more compact search spaces performed better, like the ones with those constraints, that kind of compressing reduction in the space, they did better, but maybe not as clearly or as well as you might have expected for the amount of work it was to implement some of those constraints. So let's take a look at some of these. We've got these t-test values where you say, okay, is this distribution of points on the left, is the mean of that distribution confidently, can we say confidently that the mean is higher than this mean, for example, like that the two distributions are different from each other? And so when we look at that for some of these different values, we're seeing that, yeah, in some cases, there's like very little to no statistical significance of it being different. But as we look at kind of the pattern across all of these different evaluation metrics, we see that, yes, on average, the ones with constraints tend to be more efficient at finding the high packing fractions. So that was kind of an interesting result. You know, you go in maybe thinking like, oh, well, of course, the one that like is easier to search in is going to be the most efficient. And, you know, it's so it's this kind of trade-off cost between the cost of implementation and the benefits that you're actually getting from having that. So this and many of the studies I've run are wrapped up in a material science optimization benchmark framework, where as much as possible, I'm trying to make it look indistinguishable from running the actual simulation or experiment. So kind of a Turing test of sorts, where, you know, the Turing test is, okay, if you're talking to, you know, having a conversation with a computer versus a person, can you tell which is the computer, which is the person? Make this function when you ask for a value back, make it indistinguishable as much as possible from physically running it, but at a much lower cost. And I've been summing up all of the things I've been learning about Bayesian optimization and the tools, the techniques, into one kind of teaching platform where you can kind of create your own recipe for Bayesian optimization to generate a script. So you say, I want something that has one objective, it's a multiple fidelity problem, it has constraints, it has categorical variables. You go, you click what features are there, and then it populates a script that you can then take and adapt to your own use case. It's the way I thought of, the best way I can think of to try to make these techniques that may have a multi-year startup cost for a lot of people, especially if you don't have the data science background. It's probably more in the order of months to a year, even with a data science background for some of these, to try to reduce that barrier as much as possible. This has also resulted from me acting as an informal unpaid consultant for a few dozen projects that people regularly contact me about, saying, hey, I noticed that you do blank with Bayesian optimization. Can you meet for an hour and help me develop the script or other things? You know, and so this was kind of my way to package that all up a little bit better and maybe make it so somebody doesn't have to spend a few hours. I don't really want to spend all my time doing that consulting. So here's a tool that will take care of a lot of it for you as well. Moving into the last piece, and we're seeing the X sucks, yeah. Moving to this next piece, and I think self-driving laboratories, these systems that combine artificial intelligence with automated robotic platforms, geared towards this grand idea of autonomous discovery of new materials. Of course, autonomous once you've spent all the work to kind of ramp it up and turn the dial and let it go. But I think there's a lot of potential for this to synergize with the state-of-the-art optimization algorithms, and there are great benefits that can come from it. So take a look at this workflow again. So the self-driving laboratory is essentially to do all of this in a materials discovery framework, robotically and with AI at all points possible, with as much domain knowledge baked in kind of from the start, to ensure that it's going to be successful in how you design the initial space. And we have some different equipment highlighted in the acceleration consortium for these self-driving laboratories. And so we've got looking at synthesis of perovskite quantum dots or thin films, different flow chemistry platforms. And then kind of in the last one, you know, this mobile robot, this one being kind of like the chemcuter, you know, to run various chemical synthesis, and then the mobile robot chemist to be able to run the same sort of experiments you would in the lab physically, but with a robotic hand, which comes with a slew of opportunities and challenges as well. Those platforms, I'd be surprised if any, oh yeah, the last one broke the lab floor eventually. They had to replace some of the floor, it sounds like. So there are challenges here. And one of the biggest challenges is that those pieces of equipment are expensive and they require a lot of expertise to operate. So we've got lots of different low-cost options as well that can either be used for educational or smaller scale research applications. And these kind of range from like 3D printing, peristaltic pumps, liquid handlers. And right now, Stanley Lowe and I, we're writing together with Taylor, Helen, and Alon, this review of low-cost self-driving laboratories, where we're looking at this concept of a frugal twin. So kind of like a digital twin, but for experiments. We can have low-cost equivalents that can help you during prototyping, maybe be used to even help with some of the optimization of the high-cost ones. And a lot of these demos range maybe on average from like $500 to $1,000 to get set up with, and probably around like 5 to 15 hours of time that would be required. And one of the things I wanted to do was to have something even lower cost, even less time to set up. And so this was kind of my proposal for this toy self-driving lab demo. And I thought of it in the very data science, kind of computer science sense. What's a minimal working example for this? So something that is minimal, it's complete, and it's reproducible. And a robotic arm was kind of out for that. It's either fairly expensive or inexpensive, but requires a lot of time to set up and keep working. They're 3D printers. These have come a long way. Peristaltic pumps come into play where you can move liquids, but then you have to start dealing with motors and motor drivers. And so the idea dawned on me, LEDs, light emitting diodes. I can use this. And the task for this is summed up as, okay, let's say you have some light bulb colored purple on the left based on a mixture of red, green, and blue LEDs. How would you change the values of those red, green, and blue LEDs to give you this kind of sickly looking green color on the right? So that's the task. And the idea here being you have these dimmable RGB LEDs. You control them with a microcontroller. You measure the, sorry, excuse me. You measure the wavelengths at 8 discrete points, 8 discrete wavelengths. You have some target wavelength that you're trying to achieve. Your objective is trying to minimize the difference between what you're measuring and what your target is. You can run physics-based simulations in the background. I'll kind of show what I mean by that in a bit. And then it's this question of what method can I use to reach that target, to minimize the difference between what I want and what I'm currently measuring. Close the loop. So this one, the bill of materials is anywhere about $40 US. You can add them all in one cart on DigiKey or in a couple places between Adafruit and Amazon. As you might imagine, it's not too hard to buy some LEDs and figure out how to, get a light sensor. And so this is just kind of a prepackaged version of that. This is what it looks like on the left. You've got a Raspberry Pi microcontroller, the LED, the light sensor, and a base that gives you some other things like an SD card to store your data. And it's also kind of Wi-Fi enabled as well. So I ran this basic optimization comparison on it. Took grid search, took random search, took Bayesian optimization, compared them, and as expected, Bayesian optimization shows a lot better efficiency here for it. I wrote a simple simulation class, so the idea being you can kind of prototype it even without the hardware, or you can start prototyping these multi-fidelity optimization frameworks where you say you're trying to have a machine learning model consider both both the simulations and the experiments and decide when to run which one. And so we can take just like an LED data sheet, digitize the data, which gives us a simulated light mixture, just a weighted sum of the different LED powers, and then sample those at the discrete wavelengths that the light sensor is measuring as well. Lots of notebook tutorials. Love writing and giving notebook tutorials. And so this covers a range of topics in data management and optimization, with more to come on like workflow orchestration that are highly relevant to self-driving labs, but can be done in a hands-on fashion. So for not too much. I extended it to some liquid handling, doing color matching for liquids. This isn't this isn't new by any means, but a key point here is that this reuses much of the same software and hardware from the previous demo. And so a lot of it was just almost this like drag and drop into it. And you can kind of see that here. We're using the same control mechanism. We're using the same light sensor, and we're just adding the needed pieces elsewhere. And this is what it looks like set up. A bit clunky right now, but proof of concept at least with me in the lab. Lab mate came in, took a picture of me and said that it was my monster blood demonstration. You know, it's these like colored bags hanging up from the ceiling. It's kind of fun. But running it, you know, running that same kind of optimization comparison, you know, we've got Bayesian optimization going from, you know, just without any notion of what, you know, kind of the physics behind color is, optimizing for the color. And the idea being, you know, for problems where we don't already know the solution, what's it like to get there in kind of this dark space. And then something I'm excited about doing is taking this to a solid state demo. Most of the demos have been liquid based. So this one will have a robot arm handling tea light candle holders where colored wax will be dispensed in there. The wax will be melted, heated up, or sorry, yeah, melted, and then we measure the color, run that in a closed loop as well. From there, the dreams get bigger and bigger. The step after that is a robotic chocolatier, where you can now start to incorporate some microstructural evolution or, you know, microstructure informatics into it. The different you know, crystal types, different crystals of chocolate, and how the mixtures and the processing parameters come into there. And with that, at kind of a more finalized stage, I think it sets it up really nicely for a replacing the components, replacing the components with much higher cost equivalents using nearly identical software to control it, to optimize it for autonomous alloy discovery, which is something Raimundo Arriabe is doing. There's a number of locations where they're pursuing this fully autonomous alloy discovery, and a lot of the algorithms I've been developing are very well geared towards that and related discipline sort of thing. But starting small, prototyping, and getting bigger progressively. So 30 minutes, that brings us to the end, where here are the three core thrusts that I've covered. We've got the novelty learners with the discover algorithm, very focused on chemical composition. We have Bayesian optimization, a lot of things that would play really well into formulation-based optimization, and a number of other topics as well that synergize very well with this autonomous lab framework. And I have a few recommendations, is that you go to one of these YouTube channels. I actually helped co-develop some of the materials informatics content as the honorary TA at the time for Taylor's first course on this that he put online. And then I also developed another playlist, about 4 hours of content, entirely by me, this optimization tutorial that goes over a lot of these concepts. So kind of pick the one that seems right. And I have a single I invite you to do one of these calls to action. Either follow me on GitHub so that you can see what new materials informatics repositories are coming out. I keep very detailed tabs on what's out there, categorize it, and it's a great way to kind of get yourself into the materials informatics space with people like that. Go through one of the playlists or buy the parts for the demo, or buy one of the kits like at-cost kits that were being sold, and set it up and see what ideas kind of come from that. So that is it. Thank you very much. And I hope that this has conveyed in some sense how combining data science with these materials science optimization tasks can lead to a lot of possibilities. There's a lot of transfer, and especially bridging that gap. Can we take state of the art from other domains and bring that in a really powerful way? Kind of like what we're seeing with some of the large language models, with just generation of large infrastructure simulations. Can we bring that all together in kind of this autonomous, optimized material discovery sense?
Yeah, I'm going to clap because it's a fantastic job. We're going to open up to questions. We've been sort of peppering you while we go, so I don't know how many are left, but we have time to answer some questions, and then we'll turn it over to the committee for additional committee-only questions afterwards. So to the general audience, ask away.
I got a question in terms of featureization when doing Bayesian optimization. So a lot of the issue tends to for your problem. So how do you go from like a composition to like trying to featureize your chemical space? Because it increases the space by a lot versus when you're just looking at, say, 5 to 10 space.
So what I'm hearing is like the featureization. How do you, within Bayesian optimization, how do you incorporate features? So instead of just saying like, I've got 40 ingredients, the algorithm knows nothing about how those ingredients are related to each other. Instead, you say, like, here are some physical characteristics associated with each of the ingredients. Is that what you're referring to?
Yeah, one of them was trying to use FTIR, but FTIR is like, 4,000 points. So it's a bit difficult, something I played around with. So I guess that's the motivation behind that question, or like, how do you go from just a composition to domain knowledge?
Yeah, for me, my inclination is always to put the, wherever possible, the tunable parameters that you would physically be implementing in the lab. Like, okay, I have this jar, I take this much out, like that's a parameter, like X grams of component 1. And then the other parameters being processing parameters. Now, when this becomes kind of this web of nested procedures, it gets very difficult to represent. But there are people working on that. But for me, the tunable parameters in my mind need to be there so that as soon as the algorithm suggests a new experiment, you know that you can actually go and perform that exact experiment and keep the loop closed. So I usually view it as bookends. You define your search space, you define your objectives. Everything else in between is really important, but optional in that closed loop framework. Now, if you stop there, you're gonna lose out on a lot of value that you could be getting. So things you start adding once those bookends are connected, in my mind, are contextual variables. So you say like, okay, I have some physical property that I'm not explicitly tuning. I'm not, turning up the knob on my, density filter and having something come out for like electron density. You're you're adding those variables into the model as contextual variables for it to learn from, but that it's not directly turning the knobs for it. That's my general approach to that.
Great, thanks, Lily.
I'll ask a question, Sterling. I don't know the answer to it, so it's a hard question maybe, but imagine a scenario with your autonomous labs, right? You've got these robots, but now throw in the idea of lag and latency. Will your existing approaches work for optimization? How will you have to modify them if the information feedback has real lag issues that could be over multiple length scales? How do you change your approach?
I've thought about this a lot, and it falls outside of my direct expertise, is what I've realized in a lot of ways. It's that it becomes a control problem. It's very, I would say, very well defined in one-dimensional control problems. So you've got a temperature controller and you have a power, and there's this lag in terms of increasing the power to some heating coils, or, whatever your heating mechanism is, and then the temperature that you measure, the temperature of your sample, there's that lag, there's that latency. Immediately what comes to mind is just use a PID controller. It's very easy to implement, and you'll have a very smooth way to reach your objective, your optimum, but that's for one variable. And so the real tricky issue comes in when you're optimizing many variables at once. How do you deal with that latency, that lag? And that's where I know resources to point you to, but I haven't personally implemented it. I'm interested in having other people implement that, for example, on the liquid mixing flow-based platform, because essentially what I did for that one, the optimization, is even though it was designed as a flow-based one, I kind of forced it into a iterative batch-based one. So what I did for that is I run the experiment, I let each of the dyes flow through at their power ratios long enough where I think it's kind of a steady state, at least based on, like a 5-second lag was enough to reach a fairly good steady state. So every time I do an iteration, I give it a 5-second lag. And when I'm done with an iteration, I flush it out with water until it runs clear, sort of thing. But
and then you imagine the complexity if you've got multiple processes and they don't have the same lag, right? There's different timelines. It's like your asynchronous worker problem where some are going to finish their tasks early and others what do you do with information that comes in early? Is it actionable? And how do you act on that when you're still waiting on other information? It's sort of an open problem, I think.
Yeah, agreed. And I think flow synthesis and control, control theory or control optimization come into that pretty strongly. So maybe in a year I'll have said, oh yeah, look at this this notebook tutorial.
Okay, other questions? All right, in the absence of other questions, we will now move to the non-public portion of the PhD defense. So thank you for everyone that showed up to see Sterling give his defense. You can hop off the call now.
Thanks, everybody.